composite function. So before we actually even get into composite functions, this first set of questions is asking us to address the domain of functions. Now, again, with domains, it helps to know what the parent graph looks like to a certain extent. Knowing what kind of function this is. And this first one is x squared minus 7x. So this is a parabola. And I'm just going to pull up 195. We all know what a parabola looks like. Are there any restrictions on the domain of a parabola? No, right? It's going to creep to the left forever, so coming from negative infinity, and it's going to creep to the right forever, so towards positive infinity. So the domain is just all real numbers. So we could give the domain an interval notation, which would be negative infinity to positive infinity. You may see that the domain is given by the set of all x's such that x is an element of the real number system. That would be the set notation. So interval notation and set notation. Okay? What type of function is this? When you have variables in the denominator. What's that? Dumb? Not dumb. Nothing in math is dumb. What is it? We don't know? What'd you say? Rationals. So we talked about that yesterday. Now, rationals do have limited domains, right? The parent graph, x cannot equal 0, right? That's why we have an asymptote there, yes? And visually, from the actual function itself, we know x cannot equal 0 because if it did, what would happen? Undefined. You can't divide by 0. So this is obviously a rational, but obviously also a more complicated one. But still, the restrictions on your domain come from the fact that you're not allowed to divide by 0. So our denominator cannot equal 0. Agreed? So we would set up x squared minus 2x minus 3 cannot equal 0. And we would factor to solve x minus 3x plus 1. So x cannot equal 3 or negative 1. Okay? So there's a couple ways to write this. Obviously, in interval notation, it would be negative infinity up until what? Negative 1. Then we'd close that with parentheses. A union with negative 1 to 3. And a union with 3 to infinity. So that's interval notation's way of saying all real numbers except negative 1 and 3 are excluded. We use parentheses around them. Set builder notation would be the set of all x's such that x is an element of the real number system, but then there would be a comma excluding what we could not have. X cannot equal 3 or negative 1. Okay, so again, interval notation, set notation. And this is a radical function. Now, radical functions have limited domains visually, right? We can see there's, in this particular parent graph, we cannot have any x's. The domain just is from 0 and beyond, yes? And that's because anything less than 0 underneath a radical is going to create an imaginary number, which isn't going to show up on a graph at all. So the limitation with these is that what's underneath the radical, this 3x plus 12, cannot be less than 0. That's not really a symbol in math, though. If you want to say it cannot be less than 0, then what does it have to be? Not just greater than or equal to 0. If it's not less than, that it's greater than or equal to. And then we solve this, subtracting 12 from both sides, dividing by 3. Good catch. We don't flip it, we didn't divide by negative. And so this is pretty much our domain. So interval notation, to be greater than or equal to -4, we would go from -4 to infinity. And then interval notation, we would just say the set of all x's such that x is greater than or equal to -4. And really, as far as our parent graphs are concerned, at least these, I'll bring your attention to our graphs from yesterday. There's no limitation on domains here, 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 here. There is here, we just did that one. No limitations here or here, okay? In addition to those yesterday, we obviously did this one. We just talked about the domain limitation there. We do have a domain limitation on log graphs, right? What do your x's have to be? You can't take the log of, remember from last year? You can't take the logs of negatives. You also can't take the log of 0. So whatever you're taking the log of has to be greater than 0, and you see that reflected in the graph. This y-axis is an asymptote. So it will never reach the y-axis. It just gets really, really close to it. So all your x inputs have to be greater than 0. And then obviously, if this was like x minus 5 in parentheses, and that's what you were taking the log of, you would need to set that greater than 0, knowing that you can only take the log of things greater than 0. How about this one? Any domain limitations on the exponential functions? No, right? You can plug any number in as an exponent, and you're good. How about sine graphs? Any limitation on the domain there? Given that pattern, you know, keeps going forever and ever? No. Okay? So, just thinking about what is restricted from domains there. Okay. Then on function notation, if you ever see f plus g of x, that just means f of x plus g of x. These are all pretty self-explanatory. Fg of x, multiplication, you just multiply the individual functions. Subtraction, you subtract the individual functions. Division, you divide the individual functions as long as g of x does not equal 0. Okay? Because of obvious reasons, that would make your denominator equal to 0. So we're going to evaluate some of these compositions with adding, subtracting, multiplying, and dividing, and we are going to determine the domain of the new function once we, at least in this first example, once we subtract. So we have an individual f of x function and an individual g of x function. When we subtract them, that's going to be f of x minus g of x, which is going to be 2x minus 1 minus x squared plus x minus 2. And then we simplify. Just by distributing your negative side and combine like terms. Okay, so we did a composition of a linear and a quadratic, and what was our output when we subtracted quadratic? Okay, and we all know with quadratics our domain is unrestricted, so negative infinity to infinity. Okay, and down below, I'm going to talk about this now. I have this little star. The domain is the intersection of the domains from f of x and g of x. So the domain, once you compose these functions, is going to be a result of the intersection of the two individual ones. So if you go back to this example, you can see that happening because the domain of a linear is negative infinity to infinity, and the domain of a quadratic is negative infinity to infinity. So the intersection and the overlap of those two is negative infinity to infinity. They are entirely in common, and therefore that's the domain of our resulting function. That'll get a little more interesting here because our domains are restricted in the beginning. So what is our domain of this function? X has to be what? Very good. So x has to be greater than or equal to negative 3. And how about this one? X has to be greater than or equal to 2. So the intersection of those, so here's negative 3 being greater than or equal to. Here's 2 being greater than or equal to. So the intersection of those is right here. So the domain of our resulting composition function should be x is greater than or equal to 2. Does that make sense? Okay. If we're going to actually determine what this function looks like, f of x is root x plus 3 divided by g of x is root x minus 2. That would be it. If we wanted to rationalize, we could multiply by root x minus 2 over root x minus 2. I just kind of more want to see what's going to happen here. What do we do with that numerator? Root x plus 3 times root x minus 2. Can we FOIL it? What do you think about that? What do you do with like root 3 times root 5? Do you multiply them? So do you think FOILing here would work? Like making it root x squared plus x minus 6? What do you think? Will that be the same thing as this times this? How could you test that? Because sometimes we apply properties that our gut tells us should work. Sometimes, like I'll give you a recent example on your test. A lot of people were taking this and telling me that it was 5 minus x. And that's not true. But I can see where their gut was telling them that. But how could we confirm that this does not work? Yeah. Right, plug a number in. So if I were to plug in 3, 25 minus 9 would be 16. The square root of 16 is 4. But if I were to plug in 3 here, 5 minus 3 is 2. They're supposed, if that was a good property, they would yield the same number. So let's check this one. Is this a good property? What number do we want to check? I would tell you this. Stay away from like 0 and 1 because they make crazy numbers. Who said 6? 6 is a great idea just because it's going to make this 9, which we know the square root of. And 6 minus 2 is 4. We know the square root of that. So the square root of 9 is 3 times the square root of 4 is 2. 3 times 2 is 6. So do we get 6 here when we plug in 6? 36 plus 6 brings us to 42. 42 minus 6 brings us back to 36. Square root of 36 is 6. So did that property work? It did work. So apparently, though, look at our domain. Our domain is still restricted, can only be greater than or equal to 2. Do we see that? What would be the problem with, obviously we know the, well, actually let's back up. It can't be 2, can it? Because, and this is where I wrote that in parentheses. So as long as g of x does not equal 0, unfortunately 2, so this has a little asterisk next to it. The domain is the intersections of domains from f of x and g of x, but in the case of division, that's why I put that little note there. You also have to refrain the denominator from being equal to 2. So I actually also have to write that x cannot equal 2. So our domain is just that x has to be greater than 2. What's the problem with like 1? Or 0?
You get a negative under the square root.
Good, you get a negative under the square root. Is that going to be true for, it's true for 1, it's true for 0. Is it true for negative 1? Yes. For 2. Eventually, is it not going to be true anymore, though? Like negative 5?
Yeah, negative 5 works. Negative 3 works.
Negative 5 works. 25 minus 5 is 20. 20 minus 6 is 14, and then that would seem to work. But the composition rule tells us this: the domain is the intersections of the individuals. So because this came from individual functions, where those numbers are not allowed in the domain, we cannot include them in the domain of the final. Does that make sense? Okay? So you may be able to still find numbers that work in this once you simplify it, but remember where this came from. And you cannot have anything less than negative 3 or less than 2. Okay? So this is a key point to remember. It's the intersection of the two domains as they originally were, plus the additional stipulation of the denominator can't equal 0. Any questions on that? Okay, we flip to the back. With compositions of functions, and I would think you did some of this last year, I'm not sure how much, but what does it mean to do f of g of x? Also can be written as f of g of x. You remember doing that? Yes? What does it mean to do? Adam? Correct, but it's not going to be a number in this case unless it had me do f of g of like 5 or something. Right, so finding g of x here is just taking it as it is and plugging it in to f of x. So this would be 2 divided by, we're replacing our x with 3 over x minus 1. And then we're simplifying this, and I'm going to use the least common denominator method, so I'm going to multiply the numerator by x and the denominator by x. So that's going to make 2x over, and I have to distribute down here. That's going to be 3 minus x. Now here the domain works a little bit differently. And I wrote this when you're doing compositions, f of g of x, as opposed to operations. Okay? So operations, it's the intersection. We've got that. of the two individuals. Here, the domain is the domain of g of x and its intersection with the domain of the final product. So the domain of f of x doesn't matter on its own. It's the intersection of the domain of g of x, and the domain of that is just everything except for 0, right? So the intersection of that and the intersection of this, what can x not be here? Right, so x cannot be 0 and x cannot be 3. So if you wanted to kind of look at the number line version of that, so here's 0. There's the domain of 3 over x. And here's the domain of 2x over 3 minus x. And their intersection, therefore, is everything except for 0 and 3. Okay? So your domain is, I'm going to do this one in set builder, the set of all x's such that x is an element of the real number system, but x cannot equal 0 or 3. So you might wonder, like, why is 1 allowed? Why can we do f of g of 1? And if you actually go through that process, if, like Adam was suggesting earlier, f of g of 1, the reason we can do that is because we initially are plugging 1 into g. And if you plug 1 into g, you get 3 over 1, which is 3, and then plugging 3 into the f of x function is not a problem. Right? Does that make sense? So we cannot plug a 1 into f of x. That's why 3 gets restricted. Because if we did g of 3, that's not the problem. 3 divided by 3 is 1, but that creates the 1 that we would then plug into f of x. That would make it a problem. So plugging in a 3 to the g of x creates a 1, which creates a problem going into f of x. But plugging in a 1 to g of x immediately morphs into something other than 1, so we don't have to worry about plugging it into f. Does that make sense? So this is a piece of information that you need to sort of just memorize, kind of how you get this domain of a composition versus how you get this domain of the operational set. All right? That's probably one of the more intricate details to remember. All right, and then writing our own composition. So here's h of x given to you. So they want us to express h of x as a composition of two individual functions. So let's write an f of x and write a g of x so that, and we'll just do it in this order, so that f of g of x will equal this cubed root of x squared plus 1. Any ideas here? What could the g of x function be, and what could the f of x function be, such that when we essentially take the g of x, whatever you decide that's going to be, and plug it into the f of x, you'd get that. Lily W., do you have something? Let's see how we like that. So if g of x is the x squared plus 1, f of g of x would mean take this and plug it into the x up there. Cubed root of the x squared plus 1. Good? Nice. There's one option. Anything else? What else could we do? There's definitely more than one way to do this. Any other ideas? Liam? How do we like that? If I take this x squared, take my g of x, and plug it into the f of x function, that would also give you that same thing. Nice. when you are writing these, I mean, here's one other way to do it, but I'm not going to allow it. You could technically do that, right? If g of x was just x, and you plugged that in up here, you'd get that. But when you're doing these, you need to write the composition of functions. Nothing can just plain old equal x, so don't do that, okay? Even though technically it's right, I'm going to have you come up with examples and write these under the understanding that you're not allowed to make one of them g of x, because otherwise it would be too easy. Too easy. Wouldn't make you think enough. Okay? So let's practice this. If we went with this one, what would the domain be? Take a minute. If we went with this first one, what would the domain be? Think about it. Raise your hand when you think you know. Remember this little stipulation here. The domain is the domain of g of x and its intersection with the domain of f of g of x. Just two of you? I thought you had your hand up, no?
I did.
Okay. So just Connor and Josh. All right. Let me get, oh, you think you know, Liam? Good. Okay. Let me pick on Nathan Z over there. Nathan, if you're looking at this function here, look at g of x. What's the domain of g of x? All real numbers. So you want the intersection of that all real numbers and the domain of this whole thing in its entirety. What is the domain of this whole thing in its entirety? So x cannot be 0, you're saying? What would be the problem if x was 0? What's 0 squared? Plus 1. Cubed root of 1. So that's okay. So did you mean greater than or equal to 0? Yes. So what's the problem with negative 1 then, Nathan? What's negative 1 squared? 1 plus 1 is the cubed root of 2 a problem? Nope. So did you mean greater than or equal to negative 1? Can you think of a number that would be a problem? What's going to happen, Nathan, no matter what when you square something? Positive. Plus 1 more is still going to be positive. Can you take the cubed root of any positive number? Yes, there actually is no problem there. And actually, backing up, it's the cubed root. You can take the cubed root of negative numbers if that were to have happened underneath there. That doesn't actually matter. Cubed root functions were the ones that kind of looked like this as the parent graph, right? There's no limited domain on that either. So the domain of g of x is unlimited. The domain of f of g of x is unlimited. So the intersection of that is negative infinity to infinity. And if I were to have written it this way, again, the domain of g of x coming from a quadratic is unlimited. And the domain of f of g of x is unlimited. So, again, if it's written that way, the domain would be negative infinity to infinity. Okay? Yep. Yeah, sure. Yeah. So the way that this is written and the fact that I have the f of g of x in that order kind of matches up with the way I phrase this. But just for the record, if I had it flip-flopped like this, the domain of that, whatever this is, the domain would be the intersection of the domain of f of x and its intersection with the domain of g of f of x. You kind of work inside out. Does that make sense? And the same would be true, which you're going to come across on your homework, if there's three functions, h of g of f of x. If there's three compositions, your domain of this entire thing, whatever it ends up being, is going to be the intersection of the domain of f of x, of g of f of x, and of h of f of x. You kind of work inside out. Does that make sense? The domain of h of x in isolation isn't going to matter. The domain of g of x in isolation isn't going to matter. Only the domain of f of x matters, along with g of f of x, and then with h of g of f of x, whatever that ends up being. And you want the intersection of all three of those. Is that clear? So the restriction, there is a little bit of review on composition of functions and operations on functions, obviously. But the bigger new concept is how to determine the domains of these things. Okay? So let that be your focus as far as, definitely checking your answers and making sure we have questions or clear up any uncertainties about that tomorrow. Okie doke? So there's your homework. Page 219.